In this video, we will be discussing the inner product uh, that's that's involved in Hilbert space, and uh, and this Hilbert space it's basically a mathematical tool. It's a mathematical formalism. It's a mathematical structure where vectors can be analyzed, and these vectors can be analyzed using the inner product. So this is why in this video I'll be describing the inner product, the properties of the inner product that is extensively used in dealing with Hilbert space. And particularly in physics, in quantum mechanics, this Hilbert space, what it does basically, it provides a rigorous framework for describing the quantum states, observables, and the quantum states, observables, and their interactions. The completeness ensures that all possible states and observables are accounted for making this Hilbert space a powerful tool in not only in theoretical physics but also in applied physics. So here we'll be just introducing you with the inner product of this Hilbert space. And if we choose the two elements, say u and v, this notation, what it does basically, it represents the inner product of two vectors, the inner product of two vectors, u and v, from the Hilbert space. And let me symbolize this Hilbert space as Hilbert space as H. This H should not be confused with the Hamiltonian that's generally used. So this H is a representative of the Hilbert space in this video. And if I have to define, if I start with the definition of this inner product, the inner product of this u and v is a function. This u and v is a function that takes two vectors. It takes two vectors u and v from the Hilbert space H, and it returns. What it does, it returns a scalar. It returns a scalar, a real or complex number, depending on this whether this Hilbert space is real or complex. So this H, it can be real, and it can be complex. So if we have the inner product of u and v that has been taken out of the Hilbert space, and this Hilbert space, this Hilbert space H is a real, or it is a complex, we will return with the scalar by evaluating this inner product. Now let's talk about some mathematical properties that are linked with this uh, inner product of this function u and v that I have tried to describe here. The very first important thing is the linearity. Linearity. So this inner product that we have between these two vectors is linear, and that's going to be the first argument for the inner product. And what does that mean? It means if I choose, say I have a scalar alpha, and I have described u as a vector, I have another scalar beta, and v another vector, and I have another vector, say w. And if I write down the inner product, alpha u plus beta v and w, so we can write down this as alpha, the inner product between u and w, plus beta, the inner product between v and w. For
where this alpha and beta, they are none other than that of numbers. They are simply the numbers, and u, v, and w, these are the vectors. The base, we can call them as the basis vectors of this Hilbert space. So the next important thing is conjugate symmetry. It has to be J, conjugate symmetry. Now, if we have the complex, now complex means it's enclosed by the complex functions or complex numbers, where certainly we understand that we have a linkage of that iota. So if we have this complex Hilbert space, the complex Hilbert space, then if we have to write down the conjugate symmetry, and for the inner product of u and v, we can write down the inner product of v and u bar. Where this bar, what it does, it denotes the complex conjugate. The complex conjugate. And if we have the real space, that means we are not dealing with the complex space. In that case, we can write down, in that case, the inner product of u and v is going to be the inner product of v and u. This can be exactly taken as we take in classical sense, we have the dot product of two vectors. If the Hilbert space is real, the Hilbert space is real. Now, another important property is positive definiteness. Positive definiteness. Now, if I have a vector, say, choosing my vector as u, and this vector belongs to this Hilbert space H, and one should not take this H as the Hamiltonian, it's the Hilbert space H, then the inner product of u and u is going to be greater or equal to 0. And this u will be equal to 0 only if u is equal to 0. So this is what is called a positive definiteness of the vector in the Hilbert space. So if you take the inner product of the same vector, it has to be greater or equal to 0, and it can be 0 only when the magnitude of this vector is 0. And if we go with the next important property, and that is we have the geometric interpretation of this Hilbert space. Now, if I write down angle and length, I mean, what am I trying to tell here is this inner product that we have, this inner product can be used to define the angle between two vectors. And the vectors that we have chosen here are u and v. And specifically, the cosine of the angle theta between these two vectors can be given as cosine of theta is uv divided by norm of u and norm of v. So this is our cosine of theta between the two vectors in the Hilbert space. Why this u with the double line is called norm of u and norm of v. They basically represent the length, the norm. They represent the length. So if I take the norm of u, it's giving me the length of the vector u. And if I write down the norm of v, it gives me the length of the vector v. And there is another important property that's called orthogonality.
orthogonality. Now what we have two vectors. We have chosen two vectors, u and v, and this u and v, they are said to be orthonormal if their inner product is 0. So that means if u and v is 0, then these two vectors uh, are said to be orthonormal. In geometric terms, orthogonality means the vectors that are perpendicular to each other. So if I have I cap and j cap, they are orthogonal vectors because they are perpendicular to each other. And if you take the dot product of these two vectors, they'll give us they'll come up with a result equal to 0. Now, let's talk about some examples, have some sense of some examples. The very first I would like to talk about is the Euclidean space. The Euclidean space, or to the power of n. Now, suppose we have vector u, and this vector is made of vectors u1, u2, and so on and so forth to un. And we have the vector v, and this is made of v1, v2, so on and so forth to vn in this r to the power of n. Then we can write down the inner product of these two states as u and v. And when we will have the inner product, what we'll get is we'll have u1 v1 plus u2 v2 plus so on and so forth to un vn. So this is exactly taking a situation of dot product here. So this is how we define the inner product in Euclidean space. And in complex vector space, so if I take the same thing in complex vector space, complex vector space. Now I have defined two vectors, u and made of u1, u2, so on and so forth to un, and v1, v2, so on and so forth to vn. Now this is in real space. In Euclidean space we have the real space, and here we have the complex space c to the power of n. Now in this case we can write down the inner product. So the inner product is going to be uv is summation ui bar vi. So I should run from 1 to n. So this is the inner product that's taking place in a complex vector space. And this one is the inner product that's taking place in Euclidean space, that means in real space. And this ui bar that we have introduced here, it is a representative of the complex conjugate of ui. And then let's talk about the function space. Now for functions, let us choose the function, say for example f of x, and let's choose another function as g of x. And we have a space L square of square integrable functions. The inner product in this case between f and g. So here we are talking about the function space. So if I have to write down the inner product, that will be f and g. This inner product will be defined by the integral minus infinity to infinity f of x, g of x, I should put a bar on it, t of x. Well, this g of x, what it does basically, this g of x bar, it denotes the complex conjugate of g of x that we have predefined. Now, talking about the role is important here. I mean, in quantum mechanics, this inner product that we started with as uv, which is often written in terms of the wave function or wave functions as psi and phi.
For quantum state, for quantum state of psi, and for the quantum state of phi. And so this UV is oftenly replaced by the quantum state psi and quantum state phi. And then the probability amplitudes come in action. I mean to say, when we take the inner product of this psi and phi, what it does basically, it gives the probability amplitude for a system to transition from the state psi to the state phi. So if I talk about the inner product of the state psi and state phi, what when this is measured mathematically, what it does basically is that it gives us the probability amplitude for the system to have a transition from the state psi to the state phi. And the next important thing here is the normalization. I mean, the state psi that I have defined here, this psi is normalized. What is done is it is normalized. That means if it's normalized, that means its inner product, psi and psi, must be equal to 1. And what it does basically is it ensures that the total probability that we have for the given system, this total probability is equal to 1. So these are the two important implications of the inner product that we have discussed here in this video. The inner product that takes a key role in Hilbert space. So to end this video, I would like to put a mark here that this inner product that we started as U and V, it's a fundamental tool in Hilbert space that measures the overlap between the vectors and defines angles and determines the orthogonality, and it plays a crucial role in many areas of mathematics and physics.